Swayam Prabha. Digital India. Educated India.
A logical and systematic approach to solving organic chemistry problems for CSIR-NET. In module 21, we will be looking at synthesis and reactivity of common heterocyclic compounds containing one or two heteroatoms, mainly oxygen, nitrogen or sulfur. I am Professor Balaji, currently working at Jawaharlal Nehru University. This project is sponsored by DTH Swayam Prabha, MOE, New Delhi. In this particular session, what we are going to learn is formation and reactions of various heterocyclic compounds. Let us move on to the first problem. So here the major product formed in the following reaction sequence is. So this question was asked in December 2013. An alkyne is given, alkyne keto compound is given here, and this is treated with mercuric acetate and sulfuric acid, followed by benzyl amine and heating. So these are all the two reactions that are happening, and we have product A, B, C, D, four type of products are given here, and we are going to find out how the reactions will proceed. So if you look at mercuric acetate generally converts a alkyne. Then we are going to see what is the final product, because if it is a alkene, then we know it is a hydration reaction, so that will end up with the corresponding hydroxy derivatives. And in the case of alkynes, are we going to get a alcohol or any other product? That we are going to see. So the first step is the reaction of the alkyne with the mercuric acetate. So here cyclic three-membered mercurinium ion is actually formed in the first step with the loss of acetyl unit. So this is a nucleophilic center, and mercury is a electrophilic center in this particular case. So the mercury can have a positive charge because it has vacant d orbitals, and once this intermediate is formed, this will be attacked by the nucleophile, which is water, which opens up this particular cyclic mercurinium ion intermediate. So that leads to the formation of a hydroxy unit, and again a double bond is there. So in other words, we have a enol is formed in this particular case. So when we have an enol, the enol can actually undergo tautomerization to give the carbonyl compound. So this is the first step. So in the case of an alkene, we end up with an alcohol on mercuration demercuration reaction, whereas in the case of alkynes, we end up with a carbonyl compound. So this opening of this ring actually leads to the enolic compound, and this can lose the mercury unit. So the mercury unit loss leads to the formation of a basically an enol, which can further actually undergo a tautomerization reaction to give the final carbonyl derivative, because this intermediate still has a mercury, and the mercury will be lost in that next step. So we end up with a carbonyl compound, and once the carbonyl compound is formed, the next step is the reaction with the benzyl amine. So the benzyl amine can react with this particular diketo derivative. So we have two carbonyl compound units present in this material. So when we have two carbonyl unit, the amine can react with the alkyl type ketone, and it can also react with the aryl type ketone. And of course we know the alkyl ketones are more reactive than the aryl ketone, because in the case of aryl ketone, resonance is possible. So when there is a resonance, the reactivity is going to be little bit less, because it's more stable species. When a species is more stable, it doesn't generally undergo reactions in many cases. So this particular acetyl carbonyl is the one which reacts with the benzyl amine to give the imine derivative, and this now can attack internally the electrophilic carbonyl carbon. That leads to the cyclization reaction. So this cyclization and followed by shift of bonds, because here the nitrogen during the cyclization reaction, the nitrogen had given its lone pair of electrons, so the nitrogen becomes a electropositive in nature, and we know nitrogen cannot retain a positive charge for longer time. So an adjacent hydrogen is lost with the bond polarizing towards nitrogen. Similarly, we have a hydroxy unit that is present, and the hydroxy unit can be easily lost as a water molecule. So here that leads to the aromatization of the final product. So these two loss of hydrogen and loss of one hydrogen atom and one water molecule is leading to the formation of a stable aromatic product. So these kind of eliminations happens very readily, and that leads to the formation of the pyrrole derivative as shown here. This is the substituted pyrrole that will be formed. Let us move on to the next problem. The major products A and B in the following reaction sequences are. This question was asked in December 2011. So here we have a acid unit that is present in the starting material. Alkene is also present. This is treated with the triphenylphosphine and water in the first step. Then again CbCCl and triethylamine is used in the second step. That leads to an intermediate A. This is treated with mercuric acetate followed by sodium borohydride reduction. That leads to the final product B. So if you look at acid, and the treatment with the triphenylphosphine and water generally reduces the corresponding acid unit. So if you look at all the four options, the first step is going to be the reduction of the acid unit to a amino derivative, followed by reaction with the CbCCl. That means protection of the amino unit as a CbC carbamate, and that is going to give the intermediate A. So if you look at option 1, 2, 3 and 4, the option 1 and is having a amino unit, that is the primary amino is present. So this can be easily ruled out because the second step actually leads to the protection of the amino unit. So option 1 is ruled out, and we have option 2, 3 and 4, and in the option 2 of the options we actually have a tertiary butyl ester, which is not the right one. So we can also rule out this one, and then we have only A and 2 and 4 are the only two things which are possible. And the next step is basically the final product B has only the different stereochemistry between the final product. So that means we have to see how the reaction actually proceeds, and what is going to be the, based on the starting intermediates stereochemistry, we can actually figure it out how the reaction actually will proceed. So let us look at the first step. The first step is nothing but the reduction of the acid unit by the triphenylphosphine. So this is nothing but a Schrodinger reduction reaction. So here the triphenylphosphine reacts with the acid unit, and that gives a phosphoside which loses a nitrogen molecule to form a iminophosphorine. That iminophosphorine on aqueous workup leads to the corresponding amino derivative. The other product that will be formed is a triphenylphosphine oxide, which is a stable product. So this is the driving force for this particular reduction reaction, and this is now the amino unit is protected as the CbC unit using benzyl chloroformate. So this is the second step. So we end up with the intermediate A. The first intermediate, this is the first intermediate that will be formed, and this is now treated with mercuric acetate. And when we treat that with the mercuric acetate, basically this follows a Markovnikov addition. So the internal carbon gets the hydroxy unit. So this is how we end up with the corresponding unit, and this unit actually has a nucleophilic nitrogen atom. So this nucleophilic nitrogen atom internally attacks the electrophilic carbon, and that leads to a cyclization as shown here. So in this particular case, it is the trans geometry that is happening in this particular case. So because of the presence of this nitrogen pointing towards the observer, so this attacks the hydroxy unit. So the hydroxy unit actually goes behind for the loss, because if it is in the same side, then the attack may not even take place. So that's the reason they both have to, this particular carbon has to have the trans geometry for the attack of the nitrogen atom. So that leads to the formation of this cyclase product, and here the nitrogen is having a positive charge. So this hydrogen atom is lost to neutralize the charge on the nitrogen. So we end up with the final product as shown here. So here the trans stereochemistry is present. That way we can actually say what is the correct final product be in this particular case. So let us move on to the next problem. So here consider the following reaction. We have a carbonyl compound, we have a phenyl acid. This is treated with the trifluoroacetic acid that leads to a lactam. So this is the overall reaction that is taking place. And for this reaction, the appropriate intermediate involved in this reaction is, we have 4 options, A, B, C and D. We are going to find out what is going to be the right intermediate that will be involved in this reaction. This question was asked in June 2014. So let us work out this reaction and to figure it out how the reaction actually proceeds. So the first step is the reaction of the carbonyl compound with the acid, trifluoroacetic acid. So this is a very obvious reaction. The protonation of the carbonyl oxygen takes place. So this is the first step. Once this is formed, this will now being attacked by the acid unit. So here we have a nucleophilic bond and here we have an electrophilic carbon. So the nucleophilic bond attacks the electrophilic carbon with shift of bonds taking place. This leads to a formation of a tetrahedral intermediate. So this compound is called acidohydrine. So we have the acido unit. This is acido unit, and we have the hydroxy unit. So we already know there is a N double bond N with the nitrogen having a positive charge. So this can easily be lost as a nitrogen unit, and this is the first intermediate that will be involved in the final product. So this now undergoes a Beckmann rearrangement, or this can also follow another Baeyer-Villiger type pathway. So this reaction is a very difficult reaction. This reaction is basically called as a Schmidt reaction, and this can actually follow 2 types of mechanisms. Of course, in both the cases, what is the final thing is alkyl migration takes place, and that is the most crucial one. But which pathway it follows, it may be different. So we can write both type of mechanisms to come at the same intermediate. So the overall reaction is the Schmidt reaction. So here the alkyl bond, since this is a cyclohexane derivative with no substituent, we can use any one of the bond for the shifting. So we finally end up with this particular lactam as our final product. So the overall reaction is the alkyl migration, and this reaction is called as a Schmidt reaction. So the intermediate A is this one, and this basically loses the nitrogen molecule. The driving force for this reaction, this alkyl migration, is also the liberation of the nitrogen gas. So let us move on to the next one. So here the major product formed in the following reaction is, here we have a aldehyde containing a double bond, and this is treated with this particular amino acid, and in the presence of THF, triethylamine and DMF, and this is heated. This question was asked in December 2014. We have 4 type of options given here as the expected product. Now we are going to see how the reaction actually will proceed. So let us look at the starting material, which is the amino acid. So this is nothing but the N-methyl glycine. So in other words, this is also called as a sarcosine. So this sarcosine reacts with an aldehyde. So that is the first step, and this leads to the formation of a iminium ion. So this iminium ion is formed in the first step, and we have a triethylamine which is used in the next step. We have a acidic hydrogen here on this particular carbon. There is a methylene hydrogen is the acidic one. So that is abstracted by the triethylamine. So for simplicity, the hydrogens are not shown on the carbanion. So this attacks this particular double bond, and here what happens is a 1,3 dipolar addition actually takes place, leading to the formation of a cyclized product. So a heterocyclic product is formed in this particular case, and this on heating undergoes a decarboxylation. This carboxylic acid unit is lost, so that we end up with the final product as shown here. Let us move on to the next problem. So here the right reagent combination A and the major product B in the following reaction sequences are. We are given 4 options, 1, 2, 3 and 4, and we are going to figure it out what is the reagent that is used in the first step and what is the final product that will be formed. So if we have, this is nothing but a ketoester. The ketoester is treated with some reagent and that leads to the formation of a beta ketoester, and the next step is reaction with the hydrazine. So if we look at all the 4 options, in all the 4 options we have the dinitrogen derivatives that is present here. So this is little bit difficult to rule out what is not the intermediate, and we have as reagent LiHMDS is there, so that is a base, strong base, and in the second option we are given N-butyl lithium, and in the third one we are given a lithium dimethyl silicide as the base, and the second reacting substrate is the ethyl acetate is given, and in the fourth option it is butyl lithium and ethyl acetate. So we have 2 different bases combination is given along with the either it is an acid chloride or it is an ester that is given. So we are going to now figure it out how the reaction actually proceeds. Now either it is LiHMDS, that is lithium dimethyl hexamethyl disilicide, or it is a butyl lithium, both are bases. So obviously they are going to abstract a most acidic proton. So this is step number 1. And the next step is they are going to react with the acyl unit, either it is an acid chloride or it is a ethyl ester. So either one of them will undergo a reaction that leads to the formation of a beta ketoester, and this now has to undergo a reaction with the hydrazine. So let us look at how the reaction actually will proceed. So the first step is the acidic hydrogen which is being abstracted by the base that results in the formation of a enolate anion. So once the enolate anion is formed, this can be this will react with the either acid chloride or ester. So we know chloride is a very good leaving group compared to a OET unit. So in other words, what we can say is in this particular case, acid chloride reacts much faster than the second one, than the ethyl acetate. So that leads to the formation of the beta ketoester. And once the beta ketoester is formed, this on treatment with the hydrazine gives a heterocycle as shown here. This is a pyrazole derivative. And this overall reaction is basically called as a nor-pyrazole synthesis. The various steps involved are given here. Actually, the 1,3-dicarbonyl compound is protonated in the first step. Then what happens is the nucleophilic nitrogen attacks this electrophilic carbon, and then followed by various shift of hydrogen atoms and cyclization, because the in the the terminal amine is having a lone pair of electrons. So when the second, see the first one is basically we are going to end up with the intermediate which is similar to a iminium derivative, and another second carbonyl unit has a electrophilic carbon, and that can be attacked by the terminal nitrogen unit. So that leads to the cyclization. So this is the crucial step in the cyclization, and here we have a hydroxy unit and nitrogen is having a positive charge. So it is very ready that 2 of the hydrogen atoms can be moved, that leads to the aromatization of the final product. So in other words, the driving force for the loss of water molecule and the shift of hydrogen is the stability gained by the formation of the aromatic derivative. So this is what is the overall nor-pyrazole synthesis, and we end up with a final derivative which is a pyrazole. Let us move on to the next problem. So structures of A and B in the following synthetic sequences are. Here we are given a amide having an alpha beta unsaturated aldehyde unit. This is treated with triphenyl phosphonium halide and it is heated. That leads to the formation of an intermediate A that is treated with lithium aluminum hydride, which is a reducing agent, followed by acidic workup gives a final product B. So we have 4 different options given for A and B. This question was asked in June 2015. Now we have to find it out what are all the possible product that will be formed in this particular case. Let us work out the solution. So here we have a stabilized phosphorine is used in this particular reaction. So that leads to a E-alkene. So the first step is the E-alkene formation in this particular case. So this is now treated with the, this loses the acetyl unit. So this is the most crucial thing which is happening in this particular reaction. So that gives an imine derivative as shown here. So this imine can now undergo, because we have a, this unit is basically the diene unit and this is the dienophile unit. So this can undergo a Diels-Alder reaction on heating, that leads to the cyclized product. So we have the lactam that is formed in this case. We have a carbonyl unit, we have an ester. So when we have a carbonyl unit and ester, LAH will reduce both of them. So the carbonyl unit is lost and the ester is converted to a alcohol. So this is how we end up with the amino alcohol as our final product. So this way we can find out which option is the right one for this particular reaction. Let us move on to the next problem. So the major product formed in the following reaction is, here E is nothing but the ester unit. For convenience, we have just put a shorthand form here. So an amino ester is used. There are two reactions which are happening that leads to an intermediate A and B in both the cases, and we have four different combinations, 1, 2, 3 and 4, and we have to find out what is the final product, because this is a photochemical reaction that is being used in the second step, followed by treatment with aqueous sodium hydroxide, that leads to the final product B. So we are given various combinations. Let us look at, this question was asked in December 2015. We are going to see how the reactions actually proceeds. So the first step is basically a N-haloamine formation. So here what happens is, the amine reacts with this chloroether and that leads to the formation of a N-haloamine. So this is the first step that is happening, and under acidic conditions this N-haloamine is protonated on the nitrogen, and under photochemical conditions this undergoes a homolytic cleavage. So then we end up with a chloride radical along with the ammonium ion. So these two ammonium ion is also having a radical, one electron is on the nitrogen. The chlorine is also, that means nothing but this NCl bond is broken between each nitrogen and the chlorine. So we end up with a chloride radical and the cation radical is also formed. There is a suitably placed hydrogen in this particular molecule. So this gamma hydrogen is abstracted by this cation radical. So that leads to a alkyl radical that is formed. So the conversion of the cation radical to a alkyl radical is happening. So in this particular case we still have a ammonium ion, and once a radical is formed, the next step is the liberated chloride radical from the previous steps reacts with this particular alkyl radical. So we end up with a chloro compound, and in other words we have a chloroamine. So this, in this particular case, in the gamma position the halogen is there, so we end up with a gamma haloamine, and this gamma haloamine has a chloride unit which is a very good leaving group. So the lone pair on the nitrogen attacks this particular carbon. That nucleophilic substitution leads to the cyclization reaction, and we end up with a cyclic product. The overall reaction is basically called as a Hoffman-Lafler-Freytag reaction, and the obtained product is nothing but a pyrrolidine derivative. So this is the overall reaction that is taking place. Let us move on to the next problem. So here the correct sequence of reagents for the following conversion is, here dibromo alkene is given, and that is converted to a cyclic derivative. So this is nothing but the isoxazole derivative. We are going to find it out how the reaction actually proceeds, or what are the steps involved in that. This question was asked in December 2016. So the first step is reaction with the potassium carbonate followed by a alkyne. In the third step we have a bromine. In the last step we have sodium borohydride reduction. So these are all the option 1, And in the second option B, the first step is a reaction with the sodium borohydride followed by reaction with an alkyne. The third step is reaction with the bromine, and the last step is reaction with the potassium carbonate. And in the third option, the first reaction is reaction with an alkyne followed by a reaction with potassium carbonate followed by reaction with bromine and then final reduction reaction. And D is a reaction with the bromine followed by alkyne, and the third step is reaction with potassium carbonate, and the last step is a sodium borohydride reduction. So if we look very carefully, option 1, 3 and 4, all of them have a sodium borohydride as a final step, and in the final product also we have a alcohol unit. So what we can assume is it may be the carboxylic acid unit that is getting reduced to the corresponding alcohol unit. So that means the last second option may not be the right one. And if you look at the first reagent, first one is a potassium carbonate, which is a base. And in the second B option, the first step is actually a sodium borohydride reaction. Already we know this is not the combination, so we can rule out this one. And C and D, if you look at, D also can be ruled out because the first step is bromine. Already we are starting with a dibromo derivative, and it cannot further undergo any reaction with bromine. So D also can be ruled out. And the only thing that is left out now is either A or C options. And let us look at what is going to be the reactions. If you look very carefully in A and C, the last two steps are actually the same one. That means reaction of bromine and reaction of sodium borohydride. So here also we cannot find any difference. Only the first step is the difference. That means reaction with either alkyne or with a base. That's the only thing which is different. So let us look at the starting bromide compound. Actually this is a 1,1-dibromoformal aldoxime. This starting material loses a bromide ion in the first step to give a ammonium intermediate as shown here. And this ammonium intermediate, when treated with potassium carbonate, that is a base, this hydrogen is actually abstracted. So we end up with the oxide anion. So once we have an oxide anion and we have an alkyne here, so this is a nitrile oxide and an alkyne. So nitrile oxide and an alkyne generally undergoes a cycloaddition reaction. So we can actually get, this is nothing but the 1,3 dipolar cycloaddition reaction. So here we can actually get regioisomers. If we are using a copper catalyst in this reaction, we will end up, that reaction is called the click reaction, and there is no possibility of any regioisomers. We will specifically get one particular reaction. So this nitrile oxide reacts with an alkyne to give a isoxazole derivative. So this is the crucial reaction which is happening, and once the isoxazole is formed, we have actually a acetyl unit that is present. The bromination of this acetyl unit actually happens on the methyl carbon, and we have the bromo ketone that is formed. And once the bromo ketone is formed, this is reduced by sodium borohydride to the corresponding alcohol unit. So the crucial thing will be, the first we have to treat this particular intermediate with the potassium carbonate followed by reaction with the alkyne. So that means the option 1 is the correct one for this particular example. Let us move on to the next problem. The products of the following reaction are either is or are. So the star indicates isotopically labeled carbon, and this question was asked in December 2016. And in fact, if you look at this particular problem, this is the original paper on which this particular reaction was mentioned uses the tritium on this labeled carbon. It is not the carbon which is labeled, it is basically the tritium on that carbon is actually labeled. So there is a possibility that this undergoes some sort of cyclization reaction. And in the presence of BF3 ethylate, that is nothing but a Lewis acid, it undergoes some sort of reaction and we end up with a cyclized product. So we have 4 combinations A, B, C or D. So the only difference between these two things are the labeled atoms are at different places. So that is the only thing. In option A, it leads to the formation of a 7-membered ring, and in option B, the cyclization leads to the formation of a 6-membered ring. And in C, we have both 6-membered ring formation possible. That means 2 isomers are possible during the cyclization. And in the D option, we have 2 possibilities of the 7-membered ring that is possible. So we are going to figure it out, like, what is the actual reaction that is happening and how the products will be formed. So the first step is actually the Lewis acid reaction. So here, this is the most nucleophilic one which is present here. So the oxygen now reacts or bonds with the Lewis acid, and once this is formed, the hydrogen from here, the shift of bonds actually takes place, which leads to the formation of a spiroiminium ion intermediate as shown here. So this is the iminium ion and this is the spiro junction. So this is the intermediate that will be formed in this particular step after the treatment with BF3 ethyrate. So this can actually undergo ring opening reaction. That is what we are going to see. Basically, the intramolecular reaction at the third position. So we have position 1, 2 and 3. So the cyclization actually takes place on the third position of the indole, and this leads to the formation of a symmetrical derivative. So this is a very symmetrical one, and that is the reason we can actually say it can actually open up to the next step. When we look at the next step, we will understand what is this symmetry and how we can actually predict what are the different products that will be formed. So once this symmetrical iminium ion is opened up, this can undergo a 1,2 migration, 1,2 alkyl migration. So we have 2 bonds, either this carbon to this labeled carbon is there, this bond can be broken, or the unlabeled carbon bond can also be broken. In other words, the 1,2 alkyl shift takes place and any one of the carbon can shift. That means we are going to end up with a mixture of products. So if the one which is attached to the isotope labeled carbon, if that bond breaks, then we end up with a compound as shown here that leads to a carbocation, which on losing this hydrogen atom generates or regains the aromatic nature of this particular system. So this is how the loss of hydrogen atom can take place in this particular case. So we have the labeled carbon here at the 2 position, on the 2 position, that is one possibility, and in the other case it will be happening on the 3rd position with respect to the indole moiety. So if you are labeling starting from the indole moiety, we can say this as the 3rd position is having the radio labeled or the isotopically labeled carbon. So any one of the bond can actually break, and in this particular case it is actually a 50-50 ratio of both any one of the bond can be broken. So in other words, we say the 6-membered product is the final product with any of the combination. That means either the isotopically labeled carbon can be at position 2 or it can be at position 3 of the indole moiety. So the final product is called as a tetrahydrocarbazole derivative. Let us move on to the next problem. So here the major product formed in the following reaction is, here an alkene is given. This is treated with mercuric acetate followed by reaction with the sodium borohydride. Then the 3rd step, reaction with oxygen and the sodium bromide, and in the 3rd step we are treating with oxygen and sodium borohydride. We have 4 different options given here as the expected product. This question was asked in December 2016, and if you look very carefully, the last step is a sodium borohydride reduction. So basically there may be a carbonyl unit which is reduced to this particular one. So option A has a hydroxy unit, option D has a hydroxy unit. So we can rule out B and C because they do not have a hydroxy unit. Let us move on to the how the reaction actually proceeds. So here we have a delta alkenyl carbonate that is treated with the mercuric acetate. So this forms the mercurinium ion, And once the mercurinium ion is formed, in most of the mercurinium, that is mercury 2 based reactions, there will be some water molecule that will be used in the next step to open up this cyclic mercurinium ion. But in this particular case, there is a intramolecularly the opening of the mercurinium, cyclic mercurinium ion actually takes place. So this is the crucial thing which is little bit different from the rest of the reactions what we have seen. So basically the opening up of the mercurinium ion by the alk 4-enyl carbamate actually gives a cyclized one. So here the most important thing is the trans geometry of this particular case. So here we end up with the trans 2,5 disubstituted mercuryl derivative. So here we have the mercury which is still attached to the material to the intermediate, and this on treatment with sodium bromide converts the acetate, that means simply the nucleophilic substitution of the acetyl unit takes place with the bromide ion. So the mercury bromo derivative will be there, and this on reduction with the sodium borohydride is getting converted to the hydride, or the bromine is replaced by the hydrogen atom. So that is how the reduction actually takes place. And here there is carbon mercury bond is actually present in this particular case, which is a very weak bond. So when we have a carbon hydrogen mercury bond which is a very weak bond, what will happen is basically that bond will be easily broken. So in other words, we end up with a radical on this particular carbon atom. And once we have the alkyl radical, the next step is reaction with oxygen. See, the molecular oxygen again is a diradical. We have a radical in the starting in our reaction system, and we have a diradical which is the molecular oxygen. So these two react to give the product as shown here. So oxygen here behaves like a radical scavenger, and this particular oxygen, which is a diradical, is not highly reactive towards either the mercury derivatives or with the sodium borohydride. It generally, or it very specifically reacts only with the alkyl radical, which is highly reactive species. So that leads to the formation of the peroxide as shown here. And when we treat the peroxide with the sodium hydroxide, this leads to the formation of the hydroxy unit. Here the oxygen-oxygen bond is basically broken. That leads to the hydroxy derivative as shown here. Let us move on to the next problem. So here the major product formed in the following reaction is, here amino compound is given which is treated with the sodium nitride at pH 5 to 6. So in other words, this is nothing but a diazo reaction. So we have to find out, there are 4 options are given for the final product that can be formed in this particular reaction. This is asked in December 2016. So we are going to find it out how the reaction actually proceeds. So let us look at what is the first reaction. The first reaction is nothing but the formation of a diazonium ion. That is, the amine is treated with the nitrous acid, sodium nitrate in the presence of an acid at least pH 5 to 6 means an acidic condition, leads or generates the nitrous acid, which is quite unstable intermediate. That nitrous acid reacts with an amino derivative to give the corresponding diazonium intermediate, and this diazonium intermediate can now undergo reaction, because we have a diazonium intermediate in this particular case is an electrophilic one, and we have a nucleophilic centers which are present here. So the nucleophilic center will attack the electrophilic center. In other words, this we have 2 types of possibilities that is that can happen in this particular reaction. The first one is this particular bond after the rotation, because if you look very carefully, we have a CN single bond. So we have 2 possibilities, 2 alkene or 2 pi bonds are there, and any one of the pi bond can now actually react with this diazonium ion. So which one will react? That can be decided by the next step, like what is the intermediate that will be formed after the reaction. If it is stable, then that reaction will proceed. because we can, based on the microscopic reversibility of organic reactions, we can actually say which reaction will proceed very effectively. When we have a stable intermediate, those type of reactions proceed very readily. So here if we look at both the cases, one case where the nitrogen bond without a rotation attacks this one, which leads to an unstable intermediate, because here nitrogen is having a positive charge, here again nitrogen is having a positive charge. It is not a stabilized species in this particular case. Whereas when the rotation of the CN bond takes place, when the alkene double bond actually reacts with this nitrogen, we end up with a carbocation, but this carbocation has a neighboring hydrogen atom which can be lost, which leads to a very stable final product. So in this particular case, the driving force is actually the stable product formation. So in other words, the rotation very readily takes place because that leads to a final product, final stable product. So what we can say is the attack on 2 position is not stabilized, whereas the attack on the 5 position is actually stabilized. Let us move on to the next problem. The major products formed A and B in this kind, in the following reaction sequences are. This question was asked in December 2017. So we have a beta keto ester. This beta keto ester is treated with the base sodium hydride, and bromoketone ester is actually used in the next step. Nothing but an alkylation reaction actually takes place. That leads to an intermediate A, which on treatment with trifluoroacetic acid and DCM and THF at room temperature leads to a product B. So we are going to see what are all the products that will be formed in this reaction. So first step is nothing but the alkylation reaction, and if you look at the beta keto ester, the central methylene carbon is the most acidic, it is having the most acidic hydrogen atom. So the alkylation generally will take place on this particular carbon. So in other words, we can easily rule out option 3 and option 4 because when the alkylation takes place, the bromine will be actually lost. So in other words, the option 4 is completely ruled out because that may not be the product, and option 3 also can be ruled out because here the alkylation takes place on the alkyl carbon. Of course, this may be possible, it is not that it may not be happening, but the most stable one will be the central methylenic carbon, which is also called as an active methylene unit. So that very readily undergoes reaction because the reaction is actually carried out 0 degree. So that means a more stable intermediate will be the one that undergoes the reaction. If the same reaction was carried out at room temperature or at a higher temperature, then the option A given in 3 is possible, but in this particular case it is not possible. Then we are now going to see between option 1 and 2 what is going to be the final product. If you look very carefully, the final one of the product has a hydroxy unit in it, and option B in 2 doesn't have the hydroxy unit. So whether that is a clue, we don't know, we are going to see. And we have a tertiary butyl ester, but the tertiary butyl ester is actually remaining in the final product or not is also another question we are going to look into. So that means between 1 and 2, most probably 1 may be a better option because when we work out the number of steps, we will figure it out. That is actually going to be the right product in this one. So the steps are given here, which are very straightforward reactions. The first one is basically the deprotonation of the most acidic hydrogen atom of the tertiary butyl acetate, acetoacetate takes place by sodium hydride, and the next step is basically the alkylation reactions that leads to this particular intermediate A. And now the most crucial one is the loss of this tertiary butyl unit, because this is basically called as we have a ester getting converted to a carboxylic acid. This is nothing but a hydrolysis. But if you look at the overall reaction, there is no water that is involved in this particular reaction. So this is basically called as a AAL1 type mechanism. So the driving force for this particular reaction is the formation of a stable tertiary butyl derivative. So here the alkyl oxygen bond is cleaved, and this is a unimolecular dissociative mechanism. That means the concentration of this particular species is the only thing that decides how the reaction actually proceeds. We have seen SN1 and SN2 type of mechanism. So here there is no external reagent that is involved in this reaction. So that is the reason this is a unimolecular reaction. And here the alkyl oxygen bond is the one that is actually broken. So this is the bond that is actually broken. So this leads to the formation of a tertiary butyl radical, tertiary butyl cation, and that is the driving force for this particular reaction. So this hydrolysis happens without the use of water molecule. And once this is deprotected, then we have a lone pair of electrons on the oxygen atom. So this actually makes the attack much more possible. The reason is this corresponding, we have two acetyl units. So this is nothing but a beta keto unit similar to beta keto acid, and here we have another carbonyl unit. So between these two units, this beta keto unit generally tends to remain in the enol form. So that means what we can say is this particular carbon is not going to be highly electrophilic in nature, whereas this carbonyl oxygen is a carbonyl carbon is going to be more electrophilic in nature. So that is the driving force for the attack of this carboxylic acid unit on this particular electrophilic carbon. That leads to the cyclization as shown here, and with the loss of a water molecule and the shift of hydrogen bonds leads to a aromatic structure. In other words, we are ending up with a furan structure, and moreover there is a weak hydrogen bonding that exists between the acetyl unit and the hydroxy unit that is present here. So this is how the most stable intermediate will be formed in this particular case. In other words, the furan having the acetyl unit is the first one that is the final product. So the option A is the right one, where we have the acetyl unit and the hydroxy unit, and the final product is not having the tertiary butyl unit. So that clearly tells that option B is not the right one. So let us move on to the next problems. Here the major product formed in the following reaction is, this question was asked in December 2017. So we have a substituted indole that is treated with dichloromethane and methyl lithium. That leads to four options are given for a different product that is formed. So two of them have a 5-membered ring, two of them have a 6-membered ring, and the one of the product has a chlorine which is present in this one. So we have to now figure it out how the whole overall reaction actually proceeds. So the reaction of methylene chloride with butyl lithium actually produces a chlorocarbene. So CHCl is a chlorocarbene that is formed, and this is formed by the 1,1 elimination, and this can now undergo reaction with the nucleophilic double bond, that alkene double bond. So that leads to the formation of a cyclopropyl derivative, and in this particular case shift of hydrogen atoms and opening up of the ring liberates the chloride anion. So that leads to the ring expansion as shown here. So in the final product we do not have a chloride group present. So option C is the one that is the correct one for this particular reaction.